A meteor shower is a celestial event in which a number of meteors are observed to radiate, or originate, from one point in the night sky. These meteors are caused by streams of cosmic debris called meteoroids entering Earth's atmosphere at extremely high speeds on parallel trajectories. Most meteors are smaller than a grain of sand, so almost all of them disintegrate and never hit the Earth's surface. Intense or unusual meteor showers are known as meteor outbursts and meteor storms, which may produce greater than 1,000 meteors an hour. The Meteor Data Center lists about 600 suspected meteor showers, of which about 100 are well established. Historical developments. The first great storm in modern times was the Leonids of November 1833. One estimate is over 100,000 meteors an hour, but another, done as the storm abated, estimated in excess of 200,000 meteors an hour over the entire region of North America east of the Rocky Mountains. American Denison Olmsted explained the event most accurately. After spending the last weeks of 1833 collecting information, he presented his findings in January 1834 to the American Journal of Science and Arts, published in January-April 1834, and January 1836. He noted the shower was of short duration and was not seen in Europe, and that the meteors radiated from a point in the constellation of Leo, and he speculated the meteors had originated from a cloud of particles in space. Work continued, however, coming to understand the annual nature of showers, though the occurrences of storms perplexed researchers. In the 1890s, Irish astronomer George Johnston Stoney and British astronomer Arthur Matthew Well Downing were the first to attempt to calculate the position of the dust at Earth's orbit. They studied the dust ejected in 1866 by Comet 55P Tempel-Tultul in advance of the anticipated Leonid shower return of 1898 and 1899. Meteor storms were anticipated, but the final calculations showed that most of the dust would be far inside of Earth's orbit. The same results were independently arrived at by Adolf Berberich of the K-Paragraph-Nagleisches Astronomisches Recheninstitut in Berlin, Germany. Although the absence of meteor storms that season confirmed the calculations, the advance of much better computing tools was needed to arrive at reliable predictions. In 1981, Donald K. Yeomans of the Jet Propulsion Laboratory reviewed the history of meteor showers for the Leonids and the history of the dynamic orbit of Comet Tempel-Tultul. A graph from it was adapted and republished in Sky and Telescope. It showed relative positions of the Earth and Tempel-Tultul and marks where Earth encountered dense dust. This showed that the meteoroids are mostly behind and outside the path of the comet, but parts of the Earth through the cloud of particles resulting in powerful storms were very near paths of nearly no activity. In 1985, E.D. Kundratov and E.A. Rezikov of Kazan State University first correctly identified the years when dust was released, which was responsible for several past Leonid meteor storms. In 1995, Peter Janiskans predicted the 1995 Alpha Monocerotids outburst from dust trails. In anticipation of the 1999 Leonid storm, Robert H. McNaught, David Asher, and Finland's Esko Latin were the first to apply this method in the West. In 2006, Janiskans has published predictions for future dust trail encounters covering the next 50 years. JAR copyright RA copyright by Val Balin continues to update predictions based on observations each year for the Institut de Mar copyright Conique Car copyright Lest A de Calcul des a Permil Fair copyright Mar copyright Rides. Radiant point. Because meteor shower particles are all traveling in parallel paths, and at the same velocity, they will all appear to an observer below to radiate away from a single point in the sky. This radiant point is caused by the effect of perspective, similar to parallel railroad tracks converging at a single vanishing point on the horizon when viewed from the middle of the tracks. Meteor showers are almost always named after the constellation from which the meteors appear to originate. This fixed point slowly moves across the sky during the night due to the Earth turning on its axis, the same reason the stars appear to slowly march across the sky. The radiant also moves slightly from night to night against the background stars due to the Earth moving in its orbit around the Sun. CIMO Meteor Shower Calendar 2007 for maps of drifting fixed points. When the moving radiant is at the highest point it will reach in the observer's sky that night, the sun will be just clearing the eastern horizon. For this reason, the best viewing time for a meteor shower is generally slightly before dawn, a compromise between the maximum number of meteors available for viewing, and the lightening sky which makes them harder to see. Naming: meteor showers are named after the nearest constellation or bright star with a Greek or Roman letter assigned that is close to the radiant position at the peak of the shower, whereby the grammatical declension of the Latin possessive form is replaced by id, or ids. Hence, meteors radiating from near the star Delta Aquarii are called Delta Aquariids. The International Astronomical Union's Task Group on Meteor Shower Nomenclature and the IAU's Meteor Data Center keep track of meteor shower nomenclature and which showers are established. Origin of meteoroid streams. A meteor shower is the result of an interaction between a planet, such as Earth, and streams of debris from a comet. Comets can produce debris by water vapor drag, as demonstrated by Fred Whipple in 1951, and by breakup. Whipple envisioned comets as dirty snowballs, made up of rock embedded in ice, orbiting the Sun. The ice may be water, methane, ammonia, or other volatiles, alone or in combination. The rock may vary in size from that of a dust mote to that of a small boulder. Dust mote-sized solids are orders of magnitude more common than those the size of sand grains, which, in turn, are similarly more common than those the size of pebbles, and so on. When the ice warms and sublimates, the vapor can drag along dust, sand, and pebbles. Each time a comet swings by the Sun in its orbit, some of its ice vaporizes and a certain amount of meteoroids will be shed. The meteoroids spread out along the entire orbit of the comet to form a meteoroid stream, also known as a dust trail. Recently, Peter Janiskens has argued that most of our short-period meteor showers are not from the normal water vapor drag of active comets, but the product of infrequent disintegrations, when large chunks break off a mostly dormant comet. Examples are the Quadrantids and Geminids, which originated from a breakup of asteroid-looking objects, 2003 EH1 and 3200 Phaethon, respectively, about 501,000 years ago. The fragments tend to fall apart quickly into dust, sand, and pebbles, and spread out along the orbit of the comet to form a dense meteoroid stream, which subsequently evolves into Earth's path. Dynamical evolution of meteoroid streams. Shortly after Whipple predicted that dust particles traveled at low speeds relative to the comet, Milos Plavak was the first to offer the idea of a dust trail, when he calculated how meteoroids, once freed from the comet, would drift mostly in front of or behind the comet after completing one orbit. The effect is simple orbital mechanics. The material drifts only a little laterally away from the comet while drifting ahead or behind the comet because some particles make a wider orbit than others. These dust trails are sometimes observed in comet images taken at mid-infrared wavelengths, where dust particles from the previous return to the Sun are spread along the orbit of the comet. The gravitational pull of the planets determines where the dust trail would pass by Earth orbit, much like a gardener directing a hose to water a distant plant. Most years, those trails would miss the Earth altogether, but in some years the Earth is showered by meteors. This effect was first demonstrated from observations of the 1995 Alpha Monocerotids, and from earlier not widely known identifications of past Earth storms. Over longer periods of time, the dust trails can evolve in complicated ways. For example, the orbits of some repeating comets, and meteoroids leaving them, are in resonant orbits with Jupiter or one of the other large planets. So many revolutions of one will equal another number of revolutions of the other. This creates a shower component called a filament. A second effect is a close encounter with a planet. When the meteoroids pass by Earth, some are accelerated, others are decelerated, resulting in gaps in the dust trail in the next return. Also, Jupiter's perturbation can change sections of the dust trail dramatically, especially for short-period comets, when the grains approach the big planet at their furthest point along the orbit around the Sun, moving most slowly. As a result, the trail has a clumping, a braiding or a tangling of crescents, of each individual release of material. The third effect is that of radiation pressure, which will push less massive particles into orbits further from the Sun, while more massive objects will tend to be affected less by radiation pressure. This makes some dust trail encounters rich in bright meteors, others rich in faint meteors. Over time, these effects disperse the meteoroids and create a broader stream. The meteors we see from these streams are part of annual showers, because Earth encounters those streams every year at much the same rate. When the meteoroids collide with other meteoroids in the zodiacal cloud, they lose their stream association and become part of the sporadic meteor's background. Long since dispersed from any stream or trail, they form isolated meteors, not a part of any shower. These random meteors will not appear to come from the radiant of the main shower. Famous meteor showers Perseid and Leonid meteor showers The most visible meteor shower in most years are the Perseids, which peak on August 12 of each year at over 1 meteor per minute. NASA has a useful tool to calculate how many meteors per hour are visible from one's observing location. The Leonid meteor shower peaks around November 17 of each year. Approximately every 33 years, the Leonid shower produces a meteor storm, peaking at rates of thousands of meteors per hour. Leonid storms gave birth to the term meteor shower when it was first realized, during the November 1833 storm, that the meteors radiated from near the star Gamma Lenis. The last Leonid storms were in 1999, 2001, and 2002. Before that, there were storms in 1767, 1799, 1833, 1866, 1867, and 1966. When the Leonid shower is not storming, it is less active than the Perseids. Other meteor showers Established meteor showers, official names are given in the International Astronomical Union meteor shower list. Extraterrestrial meteor showers. Any other solar system body with a reasonably transparent atmosphere can also have meteor showers. As the Moon is in the neighborhood of Earth, it can experience the same showers, but will have its own phenomena due to its lack of an atmosphere per se, such as vastly increasing its sodium tail. NASA now maintains an ongoing database of observed impacts on the Moon. Maintained by the Marshall Space Flight Center, whether from a shower or not. Many planets and moons have impact craters dating back large spans of time. But new craters, perhaps even related to meteor showers, are possible. Mars, and thus its moons, is known to have meteor showers. These have not been observed on other planets as yet, but may be presumed to exist. For Mars in particular, although these are different from the ones seen on Earth because the different orbits of Mars and Earth relative to the orbits of comets. The Martian atmosphere has less than 1% of the density of Earth's at ground level. At their upper edges, where meteoroids strike, the two are more similar. Because of the similar air pressure at altitudes for meteors, the effects are much the same. Only the relatively slower motion of the meteoroids due to increased distance from the Sun should marginally decrease meteor brightness. This is somewhat balanced in that the slower descent means that Martian meteors have more time in which to ablate. On March 7, 2004, the panoramic camera on Mars exploration rover Spirit recorded a streak which is now believed to have been caused by a meteor from a Martian meteor shower associated with Comet 114P Wiseman skiff. A strong display from this shower was expected on December 20, 2007. Other showers speculated about are a Lambda Geminid shower associated with the Eta Aquariids of Earth, a Beta Canis major shower associated with Comet 13P Olbers, and Draconids from 5335 Damocles. Isolated massive impacts have been observed at Jupiter, the 1994 comet Churyumov-Levy 9, which formed a brief trail as well, and successive events since then. Meteors or meteor showers have been discussed for most of the objects in the Solar System with an atmosphere: Mercury, Venus, Saturn's moon Titan, Neptune's moon Triton, and Pluto. See also. References. External links: Meteor showers, by Sky and Telescope, Meteor streams, 6 not-so-famous summer meteor showers. Joe Rao, The American Meteor Society, the International Meteor Organization.